Good morning to all. I am Sumitra, working as an associate professor in AAA department of Ambi Engineering College. Today, I am going to discuss about the instruction set of an 8085. First of all, 8085 is an 8-bit microprocessor, and in the previous lecture, I explained you about the architecture of 8085 processor and what all the special function registers we have there, like the program counter, stack counter, instruction decoder, instruction register, and what all the temporary registers available, and what is the function of the timing and control unit, and what is the function of the SI, that is serial communication unit and all. Everything we discussed under the architecture, and later we discussed about the pin details also. So now in second unit we have instruction sets of 8085. So before going into the instruction set of 8085, first we need to know what is an instruction. So actually speaking, an instruction is nothing but a binary pattern which is designed for each and every processor separately, and that has been designed to perform a specific function by each and every processor. So regarding this 8085 microprocessor, it will support about 246 instructions. So all these 246 instructions are classified into different types based on the operation being performed by the instructions, like arithmetic instruction, data transfer instruction, logical instruction, branching instruction, and control instruction. And we have one more classification of instruction set also, which is mainly based on the size of the instruction, mainly the single byte instruction, 2-byte instruction, and 3-byte instruction. So first, in today's class, we'll discuss about the classification of instruction set based on the operation being performed. So as I mentioned earlier, based on the operation being performed by the instructions, it is classified into 5 different types, namely arithmetic instruction, data transfer instruction, logical instruction, then control and branching instructions. Let me explain about each and every type of instructions with an example. So first, coming to the uh, first type of instruction called the data transfer instruction. These instructions are mainly intended to transfer the data. It can either transfer the data between the registers, or it can transfer the data between a register and a memory location, right? So while doing such transferring operation, the contents of the source register or source location, memory location, is not supposed to get modified. So this will be by default, the contents of the source register or source memory location will not be supposed to get altered because of the transferring operation. So we'll see one example for that. So now in this example, the mnemonic for such an instruction is move rb comma rs, or move m comma rs, move rb comma m. So first we need to know what an instruction consists of. Actually, it is consisting of some binary patterns only, but um, we can say the instruction consists of two main things, namely the opcode and the operand. So first of all, what do you mean by an opcode is? An opcode is the one which specifies the instruction that what operation it is going to perform there. And an operand is the one which specifies the data over which the operation is going to perform. So all the instruction is said to have an opcode and operand, whereas your opcode means that a function going to performed by the instruction, and operand means the data over which the operation is going to perform. Okay, so now for this example, move rb comma rs. Here rb is nothing but the destination register, and rs is nothing but the source register. And I already told you, it is not only possible to transfer the data between the register, we can also transfer the data between a register as well as a memory location, right? Here the memory location is specified with the name M, with the letter M. M means it always by default referring you the HL register path. Okay. So now for example, you consider move B comma C, right? So which means that the contents of the register C is getting copied to the B register, right? On executing this instruction, what the processor will do is it is just simply transfers the or copies the content of the C register into the B register. Suppose if the C register is having the data 04H, that is 04 in hex, the same data is getting copied to the B register, whereas the C register is also supposed to hold the same value. That is the meaning of the source register content is not supposed to get altered while transferring the contents, right? So the instruction just copies the contents of the source register C into the destination register B. This is the meaning of this instruction. And move B comma M means the memory location, whatever contents is available in the memory location pointed in the HL register pair is getting transferred to the B register. That is the meaning of this instruction, data transfer. Let me explain with another example also. MVI RD comma data. So here MVI means move immediate, right? Move immediate. What we need to move immediate? A data present in the instruction is supposed to move immediate to the destination register, right? So whatever 8-bit data is stored in the destination register or in the memory is supposed to move immediately to the accumulator. That is the meaning of move immediate, right? For example, if the instruction is MVI B, 57H, which means that the data 57 is moved immediate to the memory register, that is register B, right? The data 57H is immediately moved to the register B. On the other hand, if the instruction is MVI M, 57H, the data 57 is moved to the memory location which is specified by the contents of HL register pair, right? So it is not necessary you can move the data immediate to only the register. You can also move the data immediate to a memory register also, which is pointed in terms of HL pair. Yeah. Then we move on to the next type of instruction called the logical instruction. Arithmetic instruction. Arithmetic instruction means we can either do addition, subtraction, so many arithmetic operations are there. So whenever your processor is doing some arithmetic operation or logical operation, which flag is said to get affected? So while discussing the architecture itself, I told you that you have a flag register. One of the input to the flag register is obtained from the accumulator. Actually speaking, whatever operations are occurring in your processor is taking place only in the accumulator, and also after being performing an operation, the results also getting stored in the same accumulator, right? So the accumulator output is given as an input to the flag register, which means that the result of the arithmetic and logical operation is going to affect the status of your flag register. So we all know that the flag register is an 8-bit one, which is said to have 5 different flags, and remaining 3 bits are not in use. And the different flags are zero flag, carry flag, auxiliary carry, parity, sign, and so totally 5 flags are there, right? For example, if I'm performing an arithmetic instruction with the help of an instruction add R. So similar to that of the previous data transfer instruction, we can also add a register content to that of our accumulator, or a content available in the memory location to that of an accumulator. Suppose if an instruction is add B, after executing this instruction, the processor will just add the contents of the register B to that of the accumulator, and the result will be stored in the accumulator itself. If suppose the instruction is add M, which means that the contents of the memory register, which is pointed by the HL register pair, is getting added with the accumulator, and the same result is getting stored in the accumulator. So after adding, suppose if you are getting an auxiliary carry, then obviously auxiliary carry flag in your flag register is going to get set. Suppose after doing some operation, that is addition operation, if your result is 0, then the 0 flag will set. And after performing an addition operation, if you have even number of ones, then the even parity flag will be set. Like that, the status of the flag register will be getting affected based on the output of an each and every arithmetic or logical operation, right? So next we can move with, this is what I told you, addition with carry, right? So add the contents ADCR or ADCM, which means that you need to add the contents of the register to the accumulator with that of carry, along with the carry, right? So after doing such operation, all the flags are modified to reflect the result of the addition, whether you are getting a 0 value or whether you are getting the result in negative value. Based on that result, the respective bit in the flag register will take a 1 value or 0. That is, it can either set or reset. Yeah. And then we move on to the next type of instruction, that is the logical instruction. So logical instruction, we all know that we can either do a logical or and or not operation, or even we can complement or compare or repeat, whatever. These are all the instructions which are coming in the logical type. Suppose if I'm going to make use of the instruction complement r, sorry, compare r. CMP means compare, not complement, right? CMPR means after executing this instruction, what the processor will do is it is just going to compare the contents of your register with that of the accumulator. Or if the instruction is compare n, the processor will just compare the contents of the memory location in the HL register pair with that of the register, right? So after comparing, this result is also going to get reflected. This result is also going to get reflected in your status of your flag register. In what way means, after comparing, if you're getting your result, that is the accumulator content is less than the register or the memory content, then in that case your carry flag will set. Suppose if your accumulator content as well as the memory and register content are one and the same, then obviously you'll be getting a zero flag to be your set value. And suppose if the accumulator content is greater than the register or memory content, then both the carry and zero flags are reset, right? So it may be of the form either a compare B or compare M. That is, you can either compare a register content with the accumulator or the content available in the memory location with that of your accumulator, right? In this way, the program status register is going to get affected because of the logical instruction. And then as I already mentioned you, the logical operation means it can include your AND operation, OR operation, complement operation, like that, right? So the ORI means you will be logically ORing the accumulator with that of the 8-bit data immediately. Whenever you are having an I in your instruction in your opcode, it means that immediate, right? If it is an immediate type of addressing, your 8-bit data will be getting coming along with your instruction itself. Whatever data is present in the instruction, it will be immediately art or immediately moved or immediately exact based on the function it specifies. It is going to be the respective things, right? Suppose if the logical instruction is ORI 8-bit data, means your processor will logically or the contents of the accumulator with the 8-bit data mentioned in your instruction. For example, if it is ORI 86 means, then your microprocessor will logically add the contents of the accumulator with 86. Clear? And then based on the results, the respective flags in your flag register is going to get affected. Then coming to the next type of instruction called branching instruction. Branching means, if suppose if you want to alter the execution of certain instruction in your flow, then we need to go for branching instructions. We can go for branching either after meeting a specific condition, or we can meet the branching in some cases without checking any condition. So that's why we have conditional branching and non-conditional branching. That is the meaning. These instructions can alter either unconditionally or conditional. Conditional means after meeting the requirement, after meeting the specific condition, then the instruction sequence of the instruction will be moved to some other location, right? For example, if the instruction is JMP 16-bit address, simply the instruction is jump, but without checking any condition, means it is a jump unconditional, right? So after a certain instruction, after a certain number of instruction, if you are coming out with a jump 16-bit address, means without checking any condition, the execution of the next instruction will be in the place which is pointed in the 16-bit address. For example, JNP 2034 means automatically the processor will move on to the instruction which is available in the location 2034, right? This is what means unconditional branching, right? On the other hand, if you have this is jump on zero, not JX, JZ, right? JZ, jump on zero. That is, after performing any operation, if you're encountering a zero as a result, in that condition, the execution of the next instruction will be jumped to the location which is mentioned in the 16-bit address, right? The program sequence is transferred to the memory location which has been specified in the 16-bit address mentioned over here, right? For example, JZ 2034 means The execution will be getting transferred to the memory location 2034 only when you'll be coming out with a 0 as a result of your operation being performed by your processor. This is an example for branching instruction. Similarly, we have so many conditional branching like jump on carry, jump on move carry, jump if positive. That is, if the result of any operation is positive, then the sequence will be getting altered. Jump on minus. If the result is minus, then the sequence will be altered. Jump on zero, jump on no zero, jump if parity is even, jump if parity is odd, right? These are all the conditional jumps available in case of a processor, right? Once if the sequence is altered by means of using the jump instruction, then again we need to go back to the original. So that is done only with the help of the call instruction. Even this call may be sometimes unconditional call or conditional call. Then moving on to the control instructions. So control instructions are the one which will be, for example, if you are making use of an instruction like call, it is one of the control instruction. After your processor finishes executing the current instruction, if you want the processor to be idle for some time, then we can go with this type of instruction like halt. That is, it will remain in that state without doing any execution process. This may be an equivalent to an interrupt or reset, right, to exit from that one. Example, halt. So your halt is one of the control instruction, and NOP, that is no operand. This is also one of the control instruction. After the instruction is fetched and decoded, but till that your processor is not doing any execution operation. That is an example of control instruction. Halt, disable interrupt, enable interrupt. These are all the control instructions. So let me recap with the different types of that is different types of instructions sets available in 8085. It is of data transfer, which involves the move or load, store, or storing the accumulator content, or loading the accumulator with that of the content specified in the memory register, right? And the arithmetic and equations, arithmetic instructions include addition, addition with carry, subtraction, subtraction with borrow, increment, decrement, right? So these are all the instructions present in your arithmetic. And then coming to the logical and or XR, complement, compare, rotate the accumulator through left, rotate the accumulator through right, and all. And branch group instruction in conditional jump and unconditional jump based on the results. And then finally, control instruction means halt, no operation, push, pop, and in IO instruction means in, out. So these are all the various types of instruction sets available in 8085. So the next we'll discuss about the another type of instruction set, and also the different types of addressing modes. Thank you.